All right, so here's another conservation of energy example with whatever great, brilliant name I came up for this one. Mel, who is standing on a ledge, watch out Mel, throws a 2.10 kilogram box down toward Carla. Okay, so here's a picture of the ledge, and we've got Mel with a box, and we've got, I guess, directly below him, we've got Carla without a box. Hopefully she's good at catching stuff, right? Hope she's good at catching stuff. I see where this is going. And this is 2.10 kilograms. So let's assume that he just holds it out and drops it straight down. That's just strictly Y displacement, okay? So the height here is 12.7 meters, okay? And then, oh, you know what? This is not to scale. Not to scale. That's okay, not to scale. And then the height that she catches it, which would be like right here, is 1.35 meters. So basically, this box, is going to be dropped from there down to there, and I'm assuming she's not going to miss it, right? Mel, who is standing on a ledge, throws a 2.10 kilogram box down toward Carla. The object leaves Mel's hands at a height of 12.7 meters, and Carla catches it at a height of 1.35 meters. Calculate the gravitational potential energy of the box relative to the ground before being thrown. So we're talking about the gravitational potential energy of the box relative to the ground. Watch out, that's not the same as where she catches it. It's close, but it's not the same. Okay, so first of all, let's just do that first one. And then the second part is how fast was the box moving just before Carla catches it. So when the box gets to there, how fast is it going right when she catches it? All right, so first of all, for the potential energy, you know, potential energy, let's say initial, which is what it is up here, and that's relative to the ground, is going to be equal to m, what's the mass? 2.10 kg, is that in the right units? Yes. G, what's Earth's gravity? Oh, I'm assuming this is Earth. It doesn't always say which planet, but I guess that's a safe assumption. 9.80 meters per second squared, correct? And let's not worry about the negative or positive because we know which direction it's going. So just not to confuse ourselves, the acceleration is that way, you know that. And then what's the h? What's the h? Is it the difference between those or is it the total? Okay. So it is actually the total, the 12.7. So 12.7 meters. That's the full height from the ground. So let's just multiply these together. This is an easy one. First part is actually really easy. Potential energy initial equals, so let's see, 2.1 times 9.8, you know, you don't really have to put in the zeros, times 12.7 equals, and that seems about right, 261.3, and it rounds to a 7, joules. Okay, so that is our initial potential energy. So we might want to use that to figure out how fast the box is moving when she catches it. But no, no, no. Why not? Because actually, it's not going to use up all the potential energy. There will still be some left when it's at this point. So I can do this a number of different ways. Oh, by the way, let's put that in scientific notation. So what does that equal? PEI equals 2.61 times 10 to the second joules. So that would be my first answer. That's this answer. So let's just make sure to get that one right. Got that point, ka-ching. Now what we need to do is probably figure out what the potential energy final is going to be. Now we could do this other ways. There's a number of different ways to do this. We could start with the difference between them. But you know what I'm just going to do? I'm just going to find out what the potential energy is going to be when it's right there. Okay? Got it? So it's the same numbers. So most of those numbers are the same. Assuming that the box has the same mass, I'm assuming that Earth still has the same gravitational acceleration, right? Unless we lost a big chunk, like a continent goes flying out into space. But the new height is 1.35 meters. That is a lot less, isn't that? So my potential energy final is equal to, okay, so 2.1 times 9.8 times 1.35 equals, and what we get is 27.78 joules once again. So let's see, that's the initial potential energy, that's the final potential energy, okay? So what we have to do is find out how much energy is sort of turned into kinetic, which will be everything except for that. All of this except for that, okay? Now if we did this final minus initial, we would get a negative number, and I guess that's good because the velocity would be downward, but you know what? Let's not do that way. We got to think of this as sort of an absolute value of the energy, because when you take the square of the velocity, it messes all that up. Okay? So let's subtract these two numbers. Now normally I would do final minus initial, but I want to see the difference between these. I'm going to actually do initial minus final. Okay? So that's unusual. So one way to do this is I'm just going to change that to a negative number and then add the first one. That's a tricky way to subtract if you don't want to clear your calculator. Plus 261.37. The only drawback to doing it that way is if you make a typo, okay, it could really mess you up. So we're going to have the delta potential energy is going to be 233.59. Now the thing is, that would be negative if we did final minus initial, so that would be negative. But what's the point? We want the absolute value. So I could just write, you know, the absolute value of the change of potential energy is that. How about that? If that makes you happy. Okay. So now we know that's how much energy is going to be turned into the kinetic energy. And that's how we're going to find the velocity. That's how much energy is going to be changed by the time we get to there into kinetic energy, right? Because it's based on the difference of potential energy. Get it? So that will also be my kinetic energy final, okay? Because remember, it's a zero-sum game. So basically, almost all of this is turned into kinetic energy. That's the only amount that isn't. So this is the amount that is turned into kinetic energy. So I could just write that here if you want. Kinetic energy final equals this same number. Now I'm not putting that one into scientific notation. That's not my final answer. I'm going to write that in place, right here, in place of the kinetic energy. I'm going to write 233.59 joules equals, okay, oh, we're doing it equals in black here, 1/2, and then what's the mass again? Oh, there's the mass again, same mass. I hope it hasn't lost any mass, kg. And then v squared, well that's what we're solving for. We don't know what that is yet. So then let's see, what's 1/2 of 2.1? 1.05, right? Let's take 1/2 of that, so it's 2.1 times 0.5. This is 0.5, right? I get 1.05, of course. And it's 1.05 kilograms on this side. And on the other side, I got the same exact thing, 233.59 joules. And don't forget about the v squared, that's really what we're solving for. So now we've got to isolate our variable, get it on its own. That means we have to divide both sides by the same exact number. 1.05 kg, 1.05 kg. Okay, well that's going to cancel. And what we're going to get is a very slightly different number. Because when you divide by a number that's practically 1, it's not going to change things much. It's going to be pretty close to this. Now what I was going to do, I was going to say that if you could divide it the other way around, then do the 1 over x function. But this calculator doesn't. This is a very simple calculator. I like to sometimes use the very simple ones. It doesn't have the 1 over x function, okay, which is very convenient if you don't want to clear your calculator. So I'm just going to type in the numerator divided by the denominator, and what I get is, let's see, I get 222.47. Now what would my units be? Remember that a joule is a kilogram meter squared per second squared. And we're dividing that whole thing by a kilogram. So obviously the kilograms are the only thing that cancels there. And so what I'm left with is everything else, meters squared per second squared. And that equals v squared. Now we're running out of room down here. I think I'm at the very bottom of the field of view. I hope this is still on there. And I'm going to have to write it, when we take the square root of this, take the square root, the radical function. Let's take the radical function. We get 14, okay, so v equals 14.9, and it rounds to a 2. Now it depends on where you rounded, because if you had rounded somewhere back here, you might get a different digit in that position. That's fine. And then of course when you take the square root of both sides, that's meters per second. Okay, so what's my final answer if I want to write it in scientific notation? I know I'm doing this up at the top, but oh well. Velocity equals 1.49 times 10 to the first power. Don't forget the unit. Write your units. Meters per second. And then that's how fast the box was moving when Carla caught it. Now, if you want to describe the direction, if you're saying that this is positive, well then that would be the negative direction. So you could say this is a negative velocity. Or to make it very, very clear, you could just say downward. That makes it clear. You can describe sometimes things in words. So it's moving at that velocity down toward her. Okay? Remember, all of that came out of the stored up potential energy, got converted to kinetic energy by the time it reached her. Now the big mistake people usually make with this kind of problem is, instead of using the difference of potential energy, people use the total potential energy and convert that to kinetic energy, and of course you get a bigger answer because it's still accelerating. It would be going even faster if you let it fall another 1.35 meters. It would be going even faster on the ground when it hit the ground. So if you want to find out how fast it would be when it hit the ground, if she missed it, well then you would have to use the total potential energy, turn that into your kinetic energy, and then solve for v the same way. So that's how you do this kind of problem, sort of the Mel-Carla problem, or the, what did we use, Django-Boba problem. And I forget who else we used. Did we use Tony and Bruce problem? It's that kind of problem. It's one of those one person throws, one person catches problems. Okay, here's another problem. This is a work problem, but it's different than the ones I've shown you before. A worker pushed a cart weighing 111.0 kilograms to the top of an inclined plane. Initially, the cart was 3.11 meters above the floor. If the top of the inclined plane is 6.35 meters above the floor, calculate the work done by the worker as he pushed the cart to the top of the plane. So imagine that there is a slope. There's a slope going. The bottom of the slope is a certain height, 3.1 meters above the floor, and the top of the slope is higher, 6.35 meters above the floor. So we are going to use the equation for work, right? Because it says how much work was done. Well, here is the general definition of work, force times displacement. But you know what? We don't even know what the force was here. It doesn't really tell us, because it doesn't give anything about time. So we need something that doesn't involve time. Also, what was the displacement, by the way? If the displacement was from here to here, it doesn't really tell us what that distance is. It just tells us how far they were off the floor, like this. One was here and one was here. That's it. So we can't really use this. We better look at our equation bank for something else. Oh yeah, luckily there's more than one definition of work. There is, of course, this one. Okay? The change of kinetic energy. Okay, well that's good. But do we really know the kinetic energy at either point? Do we know its velocity? We need to know, for kinetic energy, of course, you would need to know the velocity. We don't know its velocity, so we can't use that. Forget that. Isn't there another equation for work? Oh yeah, that's why I gave you this one. Work is equal to negative change of potential energy. So whatever the change is, negative. Now the reason for that is the way we define change. Just like for anything, it's final minus initial. So one way to get around this is to do initial minus final, but I'm not going to do it that way. I'll just do it regular style and then just put a negative sign in front of it. So we're going to do it this way. Forget about this one. We're going to do it that way. I'll put it over here. Okay? So in order to do that, we need to know the potential energy. If we're going to do the change of potential energy, we have to know the potential energy. We have to know the potential energy initially and at the end, initial and final. So let's get going. I'll move this down. All right, so potential energy initial equals, well, mgh. What's the m? That's easy. 111.0 kilograms. Okay, what's the g? Well, I'm assuming this is Earth. If they ever don't tell you in a problem what planet it is a good assumption to assume that it's Earth, meters per second squared. Oh, wait a second. Doesn't gravity accelerate downward? Oh yeah, that's negative. That's negative. Let's just leave that in this time. Because in this case, it might be significant. Okay, and then the h. What's the initial height above the ground? Initially, the cart was 3.11 meters. So let's just multiply that together to save time. Let's just do this one first. 111 times, well, it's negative 9.8 times 3.11. Positive times a negative times a positive gives me what? Gives me a negative. Okay? And what I get is 3383.06. 3,383.06 joules. All right, so now let's do the potential energy final. Okay, what it is when it's at the top of the slope. Remember, once it moves up the plane, everything else is going to be the same here. It's going to be the same mass. I don't think the box has lost any mass. Okay, I don't think that the Earth has any difference in its gravitational attraction, even though it doesn't tell me how much time. I guess theoretically, if this was over billions of years, well then maybe something collides with the Earth, changes its mass, changes gravity. I don't know. But that's unlikely, very unlikely. Let me move this down. And then we need the new h, which is 6.35 meters. So again, it's positive times a negative times a positive. And we're going to get PE final equals, now let's multiply them. Again, 111 times, it's negative 9.8, times 6.35 equals, well again, positive times negative gives me negative. And then I get 6907.53 joules. So what is delta potential energy? What is the change of potential energy? It is final minus initial. So it is negative 6,907.53. Probably don't need to keep it this exact, but whatever, okay? Final minus initial, which is negative. See how tricky negative signs can be? Because it's final minus initial. So we're subtracting a negative. Oh boy, 383.06. Now usually we get negative numbers wrong, but there's just a higher error rate. There's just more likely that you're going to do something wrong. So subtracting a negative is like making it a positive, right? And so I could write this the other way around. Why don't I just do that? Okay? Now this is still just for regular potential energy. This is not negative potential energy. I'm solving for regular difference of potential energy. So I'm going to rewrite it because this becomes positive and this one remains negative. So I'm going to write this one first now. See what I'm doing? Minus that. So see what I mean about how saying one way to fix this problem of having it negative is to do initial minus final. It's sort of like what we're doing here. But actually, all I did was minus a negative makes it a positive. So it's a lot easier to just have a positive minus something than a negative minus a negative. It just gets confusing, right? So what I'm going to do is 3383.06 minus 6907.53, and what I get is my delta PE. Of course it's going to be a negative number, isn't it? Because this one's bigger. Negative 3524.47 joules. I almost made that a J. So that is my delta PE. But what about my work? My work is my negative delta PE. Uh-oh. So then all I have to do for my work, let's write that in a different color. Work, oops, equals, change the negative to, what's the negative of a negative? It is a positive 3,524.47 joules. Same number, but now it's positive. See why they have that? That's why they have that. Because obviously he did work, he moved the object upward, he increased its potential energy, he did positive work, right? Get it? Of course we want to put that in scientific notation. So let's do that as our last step. I think I can still fit it on here. W equals, I can still put the positive, 3.52 times 10 to the, how many places do I have to move this? 1, 2, 3, right? Whenever something is in the thousands, you always have to move it 3 joules. So then that would be how much work the guy did. And hopefully this is all on the screen, but I'll just slide it up just to make sure. So these are my last couple steps in case they were going off the bottom. Okay, so notice this was my delta PE, but because the definition is negative delta PE, I had to take the negative of a negative, making it a positive. Okay, and then of course I just had to put it in proper scientific notation. One thing I want to mention here, in case you'd rather do it the other way, let's just do it the other way here, in case you don't understand what I did here or don't like it. Okay, let's do it this way. Now we got to put these numbers in negative this time. So 6907.53. Now I have this on my calculator. I'm going to hit the negative sign. Now it's a negative. And I'm going to hit minus, I'm going to type this number in, 3383.06. I'm making that number negative, equals, and I get the same answer. So you didn't really have to rearrange these. I just think of it, it's easier to think about something minus something else instead of a negative something minus a negative. I just think that that is a little confusing. So notice that these would combine to make it positive, so I put that to the front. And it doesn't matter which order of operations you do. So we didn't actually subtract initial minus final. So let's see how that works out. 3383.06 negative, right, minus 6907.53 negative equals, and what I get is my positive answer, like this. So that works, okay? So you can think of doing a negative change. You can do initial minus final. Takes care of that, okay? If it's that would be the negative change, okay? The regular change would be final minus initial. Okay, so that's another way to think about it. Because remember, whenever we define delta, it's always final minus initial, over and over, right? Okay, so that's how we do the kind of worker problem on an inclined plane, or like the scroll problem maybe. And he really did work. He gets a paycheck for this. He did some positive work. He gets real money, positive money. Here's one more example of how to do work, get some work done. Leah and Han drag a box of mass 30.2 kilograms along a frictionless floor. Well, that would be nice, wouldn't it? Leah pushes the box with a force of 28.2 newtons. Han pulls the box from the other side with a force of 33.6 newtons. What is the net work done on the box if the displacement of the box is 22.2 meters? Okay, so notice that there's a box there's a box, and Leia is pushing the box, and Han is pulling the box, so those forces are going in the same direction. So to get the force, if we were going to do work, we're going to use the regular work equation, the one that's right there, okay? We need to know the force first, right? Well, it's actually the combined forces, all right? So what are the forces? Well, there is 28.2 newtons, and let's just say that's positive direction. Let's just keep things positive. Plus 33.6 newtons, and let's say that's positive. So what does that equal? I'm writing my n's really big for some reason. 28.2 plus 33.6. I guess Newton was an important guy, but maybe I'll start writing them smaller anyway. 61.8 newtons. That's the way I usually write it. All right, so now we know the force. So let's just say that was my force total. Okay, that's my F total, is this. So add them together. And of course, hers was pushing 28.2 newtons, and his was pulling 33.6. So see how those add? Because they're both, here's the center of the box, she's pushing it, he's pulling it, and this would work if this was like C3PO or whatever. So that's pretty easy. Then if work is FD, then let's see. If work equals FD, then why don't we just have W equals, well, there's my force, 61.8 newtons, positive newtons, times the displacement. So don't you think the box is going to be moving that away? And if it moves from here, 22.2 meters that away, that's a positive displacement. So 22.2 meters. This is not a hard one, is it? Not really very hard. So 61.8, I even still have that on my calculator, times 22.2 meters equals, color, I'll just do it in black, W equals 1371.96. Now we're doing work here, and it's newtons times meters. So maybe you're losing track of what the units should be. Remember, a newton is a kilogram meter per second squared, and then we're multiplying that times meters. So that would be kilogram meter squared per second squared. Oh yeah, how do we write that? Joules. And don't forget that work has the units of energy, because remember that some of the ways you can define work are as a change of energy. So it better have the same units, right? First, let's put that in proper scientific notation. Equals 1.37 times 10. By the way, this was the thousands place, so to move it to there, 1, 2, 3, 10 to the third joules. So that would be a pretty good way to answer this problem. But what if this was, for example, like a power problem? What if they did this? This doesn't tell me how long it took. So depending on how long it took them to do this, okay, it could be different amounts of power. So let's just say if this took, if it took 1 second, let's just make the easy example, then I would divide this. I would do power equals 1.37 times 10 to the third joules over 1 second. And then of course, that wouldn't change the number, but then it would be, remember that a joule was a kilogram meter squared per second squared, but then it would be a kilogram meter squared per second cubed, okay, because we're dividing by seconds again, and that turns out to be the units of the watt. So it would be the same number as here. It would be, the power would equal 1.37 times 10 to the third, but now the unit is watts. Isn't it funny that the unit for power is watts, is a W, and the unit for work is joules, and the unit for force is newtons? All of these are proper names. All of these were great scientists and engineers that made breakthroughs that led us to the world we have today, okay? But what if it took, I don't know, what if it took 2 seconds? Instead of 1 second, well then we would divide this by 2. So what's 1.37? 1.37 divided by 2, okay, 0.685. So it would be the same number, but it would be 0.685. I'd have to move the decimal back. So if it took 2 seconds, I guess I have to write it over here if you can still see it, the power would be different. it would be 6.85 times 10 to the second watts. So notice the point is the power depends on time. These are not really in the problem, in the question. I'm just showing you that power depends on time. Work does not. Work is the change of the energy that you've accomplished, no matter how long that took. So if you want to talk about work based on these definitions, think of it that way. It's how much change of energy you have accomplished. It doesn't really have the time in here. Now, technically, you could extract the time from the velocity. You might be able to figure out a way to extract the time. Okay, but in the actual calculation, time was irrelevant. Okay, so you get the same amount of work done if it takes you 1 second or 2 seconds. I could have done an example where it took me an hour. Okay, what the heck, I'm just going to do that one just to show you. So remember, if we're calculating power, we know how much work was done. We've done that already. But if we want to know how much power, well, that depends on the time. So what if it did take them an hour to do this? Because it doesn't say how long it took. Okay, well then power, I'll make that blue, power equals work. Here's the number for work right here. I'll just make that black. 1.37 times 10 to the third joules, and then over time. Well, what would it be if we had an hour? Okay, if we had an hour. Well, an hour is 3,600 seconds. Why? Because there's 60 minutes in an hour times 60 seconds in a minute, 3,600, right? So what if I put that, let's just put that in scientific notation. What would that be? That would be 3.60, I'll just get rid of that 0, times 10 to the, what is it? 1, 2, 3. Interesting, they're in the same sort of order of magnitude. They're in the same ballpark, as they say. And then that's seconds. So basically, if I take 1.37, it's funny because when these exponents are the same, you can kind of ignore them. It's just this division. Whenever the exponents are exactly the same, you know they're going to basically just cancel out. Okay, because these are both in the thousands. So 1.37 divided by 3.6 equals 0. And I'm solving for power, so I'll do it in blue. Power equals 0.38, and if I round it, it's a 1. Okay, and 10 to the third divided by 10 to the third, 3 minus 3 is 0. Okay, so this would be times 10 to the 0, but it's actually just this number. Okay, if you want me to keep that, I will, just to, so you can see what's happening here, 10 to the 0. And then joules divided by seconds. So that's like kilogram meters squared per second squared divided by seconds. Oh yeah, that is a watt. Now we've got to fix into proper scientific notation. So the power equals 3.81 times 10 to the, look what we did there. We moved the decimal that away. So what does that do? Makes it -1 watts. So look at the difference if we do the same amount of work, the exact same amount of work, but if we do it in 1 second, it's 10 to the third watts. Just look at this part of it, okay? And if we do it over an hour, it's 10 to the -1 watts, okay? Less than 1 watt. Interesting, right? So it makes a big difference the amount of time, and that's why power is so important. It's how quickly the work is done, over what period of time. Okay, so that's another example. Boom.